Chali, Namaskar everybody, good evening all. I welcome you all on the behalf of StudyIQ IS. My name is Pritesh Mathurkar. I am the Senior Faculty of Geography, Environment and Ecology in StudyIQ IS. And side by side, I am also your official tour guide because the person which all of you are seeing on your screens right now, I have traveled across 48 countries of the world and I have been to 4 continents of the world per se. So I just don't teach geography, but I also live for geography. So guys, welcome to the crash course, the most ambitious one ever taken on YouTube, wherein different faculties are going to come and they are going to discuss and decode some important topics which are mentioned in your civil services examination syllabus from a mains perspective and also including the current affairs. So those of you who are watching me live right now, feel free to comment because yes, I am live right now. So any difficulty you are having, you can also ask me. Rest of you, those who will watch me in a recorded format, please understand that this is a mains crash course. So here I am taking the leverage of you having done the prelims part properly. Prelims part properly in the sense that I'm hoping that your basics are done so that I can build up on the advanced concept which UPSC is typically framing. So today's lecture being on the important geophysical evidences, today's lecture being on the important geophysical phenomenon, and today's lecture being on the important geophysical applications of some of the important tectonic activities that we have, on some of the important climatic abnormalities that we have, and some of the abnormalities which we are finding in the oceans. So in today's lecture, I will be traversing across different spheres of geomorphology, of climatology and oceanography. I will be painting in front of you all different locations, different interpretations, and also in front of all of you I'll be opening up some good diagrams which you can very well use in your mains too. So let us begin our today's journey. Hope all of you will appreciate this and all of you will enjoy this journey. So in today's session we are going to discuss important geophysical phenomena. So precisely which important geophysical phenomenon we are going to discuss. So the favorite ones of UPSC, we will discuss what is volcanism, what are its associated landforms, because landforms questions, they are now being repeatedly asked from last 3 to 4 years. So exogenetic landforms UPSC has focused on. Today I'll be focusing on the little bit landforms which are created as a result of endogenetic processes. We'll be trying to decoding, sir, what are basically the earthquakes, but again from a mains perspective. Then number third, I will be focusing on a very important topic of today, which is basically cyclones. So cyclones, I'll be discussing both the temperate as well as tropical cyclones, because from this is where now UPSC is framing majority of the questions from last 3 to 4 years, both in prelims and mains. So both temperate and tropical cyclones will be discussing. Then number fourth, I'll be venturing out into the part of oceanography. I'll be discussing with you all what are the marine heat waves. Some recent data I will be putting in front of you. Plus we'll try to understand what is coral reef bleaching, because now this is a very hot topic which UPSC has not yet framed in the mains. So this question can come, and side by side I will just give you a hint with regards to India, in the sense that now this is a kind of hot topic for UPSC. When I'm talking about India per se, so the climate of India, the variations in the different parameters that we have in India, so based on that, how we are having the altitude based zonation, how we are having the latitude based zonation of vegetation and wildlife also. So we'll just try to basically paint a good picture of all of this. So those of you who are watching me live right now, I guess few people have joined. Please feel free to comment and take this as your regular lecture, but little bit on the advanced part. And dare I say, I will try to give you as much information as possible from my end in this limited time slot. And it will be my pleasure that I will be able to highlight each and every term in front of you. It's your take now how much of this you actually digest in this time, and most importantly, it's your take as to how you capitalize on this, because see, the knowledge is of course infinite. we have to concise the knowledge, and most importantly, we have to understand the application of it. Okay, so let's start. So if I'm starting off with the very first topic that we are going to discuss, it is basically the volcanism and earthquakes. So typically speaking, volcanism and earthquakes is taught from, sir, how do we have the seismic wave based analysis? Sir, these are the types of volcanoes, this is that stuff. But I'm going to discuss this from a different perspective in the sense that we'll try to understand what are basically the landforms which are created using basically volcanism and earthquakes, predominantly rifting and faulting, because now we are witnessing numerous rifting process going on. Like let's say the Africa is splitting. In India also, we just now witnessed the inauguration of Chenab Bridge. So Chenab Bridge lies in the main boundary fault or the main transform boundary of basically the Himalayan belt, where you are having numerous of reverse faults out there. So we'll try to decode all of this using basically the discussion of landforms per se, and then we'll slowly build upon all our concepts. So if I'm talking about landforms, guys, typically the landforms are classified into two parts. You have structural landforms and then you have erosional landforms. Structural landforms basically meaning such landforms which are created due to endogenetic processes. So we can have the structural landforms created because of plate tectonics. So as my colleague Bhuvan sir has already enlightened in front of you some of the landforms created as a result of plate tectonics. So you can have basically the moor location, the mid-oceanic ridges. You also have the trench locations, and then you also have basically the sea mounds and geodes. So the world's tallest peak, the world's tallest mountain measured from its bottom till top, Mauna Kea and Mauna Loa, the tallest peaks on earth. Remember, the tallest peak on earth is not Mount Everest, it is Mauna Kea and Mauna Loa, where you are having Hawaii, Honolulu. So I don't need to elaborate on that, but we need to elaborate on the process of volcanism, because this is where now UPSC can frame the questions. And of course, we have the landforms created because of rifting and faulting. So now this is a very unique area and the area of focus for UPSC, because we have to understand the associated earthquakes, we have to understand the associated process with regards to this. So we also have the landforms created because of erosional agents like wind, water, glaciers, groundwater. So I guess all of you are smart enough to understand that, and it's very well mentioned in NCERTs also. So we don't need to focus on that. We need to focus from wherein UPSC can frame this year's question. So now let us start to move ahead and let us start to understand the first kind of interpretation. So if I'm talking about volcanism, so what exactly is volcanism, guys? So volcanism is basically the process in creation, movement, eruption, and the eventual solidification of magma/lava. If the volcanic material is solidifying inside the earth itself, we will refer to it as magma. If it is solidifying outside the earth's surface, we will call it as lava. So if we are trying to understand the landforms and the associated process of volcanism, first we have to understand the different types of volcanoes that we have. So the volcanism or the different types of landforms can be classified into four types. So four types in the sense of what? So the four types include that number first, we can classify them on the basis of periodicity of eruption. Periodicity of eruption meaning whether they are active, whether they are dormant, or whether it is extinct. So in a nutshell, if I'm talking about active, dormant, and extinct volcano, so active volcano in the sense that you are having a volcanic crater above, below it you are having the vent, and below the vent you are actually having the magma chamber. So this magma chamber, if it is supplied with fresh magma continuously, or if it is supplied by fresh magma not continuously, but let's say once in 10 years, once in 20 years, but the magma chamber is existing, the central vent is also existing, then we call this as active volcano. Then we can have dormant volcano. Dormant volcano in the sense that the central vent is existing, the magma chamber is also existing, but the magma chamber is not basically supplied with magma in the past 50 years or 100 years. So then we call it as dormant or sleeping volcano. And we can have extinct volcano, where the magma chamber has collapsed, the central vent has also collapsed, and now above you are having a big volcanic crater wherein you can have the accumulation of rainwater. And if the crater becomes too big, we call it as caldera. So some of the world famous calderas that we have, so we have a very huge caldera in New Zealand. So if I'm taking you to New Zealand per se, on the northern island of New Zealand, here we are basically having two very important calderas. So in the northern island of New Zealand, you have Lake Tekapo. No, Lake Tekapo is in the southern island. In the northern island, you have basically a lake called as Lake Taupo in the middle out here. You'll be able to see it on the screens also. So over here, you have Lake Taupo. And then above, you are having Lake Rotorua. So Taupo and Rotorua, they are very big volcanic calderas that we have in New Zealand. So this is basically the classification on the basis of periodicity of eruption. But using this, we are not able to fathom. The second one we can have, it is on the basis of type of magma associated. Type of magma associated in the sense that we can have andesitic magma, we can have basaltic magma. So basaltic magma, as you all know, it basically flows like a river. Why? Because basaltic magma is extremely fluidic. It is having very less proportion of silica. So as your silica proportion decreases, the viscosity of the magma also decreases. So as the viscosity of the magma decreases, the magma, it starts to flow like a river. Whereas on the other hand, if I'm talking about andesitic magma, the circum-Pacific belt of volcanoes, the circum-Pacific belt of earthquakes, we call it as PROF, Pacific Ring of Fire. There you are predominantly having andesitic eruptions. So the andesitic eruptions become very violent. Why? Because the andesitic magma is viscous. It is very viscous. It is having a higher proportion of silica. That is why it flows not smoothly, but it basically flows in intervals. So it flows, it stops, it flows, it stops. That is why wherever you are having andesitic eruptions, such eruptions, they become very, very explosive. But using this, we are not able to decode anything. So now let us move towards the best understanding of volcanic distribution and the best understanding of volcanic landforms. So we can basically discuss the volcanoes on the basis of intensity of eruption. That how does your volcano actually erupts. So the basis of intensity of eruptions, we typically are having 5 classification, but you don't need to remember the 5th one because it's purely a research kind of classification. For GS perspective, you only remember 4. So we have the Hawaiian type of eruption, then we have the Strombolian type of eruption, we have the Vulcanian type of eruption, and the most deadliest, we have the Pelian type of eruption. So we have Hawaiian, Strombolian, Vulcanian and Pelian type of eruption. So can we just have a distinction among all of this? Yes, definitely. So if I'm talking about Hawaiian eruption, so all of you know that Hawaii is basically a volcanic hotspot. So if I'm just showcasing you the Hawaii eruption, so Hawaii eruption is where you will be able to see the magma or the lava basically flowing like a river. So see, this is how you are having the eruption of Hawaii, wherein the lava basically flows like a river. Why? Because Hawaii is a hotspot. It's a deep mantle plume. So the lava which is sourced at the Hawaii, it is coming from the mantle core boundary. And we all know as we grade down in the mantle core boundary, the silica proportion decreases. And that is why the Hawaiian eruptions, they become very fluidic. The lava, it starts to flow like a river. And that is why the Hawaiian eruptions, they become the quietest eruptions of all. You are having ultramafic basaltic magma which flows like a river. Therefore, these eruptions become the quietest eruptions that we have on Earth. After that, we do have Strombolian type of eruption. So Strombolian type of eruption, it is named after Mount Stromboli. So if I'm just showcasing you where is actually Mount Stromboli. So Mount Stromboli is on the west side of Italy, and Stromboli, it is referred to as the lighthouse of the Mediterranean. And as I'm taking this lecture, Mount Stromboli is very notorious. So Stromboli erupted just 2 weeks prior. So if you carefully observe Mount Stromboli, so Mount Stromboli is referred to as the lighthouse of the Mediterranean. It has been used as a navigational waypoint since centuries, since ages. So if you carefully observe the eruption of Mount Stromboli, guys, you will see a very unique peculiarity. What is this unique peculiarity? So here you are not having that much eruption of magma. So here more steam and gas is coming. So you are having more steam and more gas coming. You can have sulfurous gases, you can have nitrous gases, you can have CO2 also coming. So if I'm talking about Strombolian type of eruption, where you are having more steam and gas being erupted, we referred to such eruptions as phreatic eruptions. So please remember that such eruptions, they are referred to as what? They are referred to as phreatic eruptions, where instead of magma, more steam and gas are erupting. And now this is a very, very important current affair for 2025. So those of you who will be giving mains this year, we need to understand that the deadliest eruption in terms of intensity. Please understand and appreciate this. See, when I'm talking about deadliest eruption, you can quantify it into two parameters. First of all, the eruption on the basis of basically how much people died or how much matter was actually ejected. So if you understand and appreciate, sir, which is the deadliest eruption to take place up till now. So the deadliest eruption in terms of ejection of matter happened in 2022 and 2023, which is referred to as the Hirunga Tonga or the Hunga Tonga eruption in the Southwest Pacific. Why? Because this was the only eruption in the history of mankind where basically the steam and gas, it reached into the stratosphere. So if I'm showcasing you the Tonga eruptions photo, so this is basically the deadliest eruption ever captured by mankind. And if I'm talking about this Tonga eruption, so this Tonga eruption was clearly visible from the space also. So see, this was the photo captured by the International Space Station. So this is very, very important. Yes, good evening Kanwar ma'am, good evening Nimisha ma'am. Hope you are able to listen to me very clearly. So this being a mains crash course, so that is why I am going with a good pace so that I can cover as much topics as possible for each and every one of you. So these are referred to as what? These are referred to as phreatic eruptions. You are having more steam and gas coming. So please remember this. After this, basically, we are having the next type of eruption. We refer to it as the Vulcanian eruption. So Vulcanian eruption meaning that here you are having very thick, very pasty, viscous magma. A viscous magma in the sense that it is having very high content of silica. So as the magma becomes andesitic, as the magma becomes viscous, you basically are having the formation of lava bombs. So volcanic eruptions, they are named after Mount Vesuvius. If I'm showcasing you where do we have Mount Vesuvius. So Mount Vesuvius is located again on the west coast of Italy, and it is world famous because at the foothills of Mount Vesuvius we are having Naples, we are having Napoli, right? So if you carefully observe this image, if I'm just opening up this image for all of you, so this is your Mount Vesuvius, and the city which you are finding over here, this is the town of Naples, the birthplace of pizza, right? So there was a city over here which was basically completely destroyed due to the eruption of Mount Vesuvius. That city's name was Pompeii. So why is this eruption so peculiar? You will be asking me. So I will say that this eruption is so peculiar because here you find basically the formation of what? Find the formation of lava bombs. So thick lumps of pasty magma, thick lumps of basically pyroclast along with molten rock which get accreted together to create such lava bombs, and that is why such eruptions, they become most deadly. But now if I'm talking about in sense of, sir, the eruption of lava and the associated with it the loss of human life, so the deadliest eruptions, we can say they are referred to as Philian eruption. So the geologists, they also referred to this as the Philian, Philian, but for our understanding, we'll be referring it to as Pelian eruptions. So Pelian eruptions, they are referred after Mount Pelée. So Mount Pelée is basically a volcano on the island of Saint Martinique in the Caribbean. What is the peculiarity of this kind of eruption, guys? The peculiarity is that here you start to get granitic incursions. Granitic incursions in the sense that along with andesitic magma, you have little bit mixing of granitic magma also. So you very well know if granitic eruptions start to occur, then it's like the call of God, because the temperatures are very high and the lava, it basically stops flowing. So that is why it starts to heat up the local atmosphere and starts to heat up the surrounding regions like anything. So if I'm trying to showcase you Mount Pelée, how does Mount Pelée look like? So this is how your Mount Pelée basically looks like. And associated with it, we are basically having the deadliest eruption ever to occur. Deadliest eruption ever to occur in the sense of the loss of human life. So this is your Mount Pelée, a mountain, a volcanic mountain in the Saint Martinique group of the Lesser Antilles in the Caribbean. And associated with it was basically the very infamous eruption of the Krakatoa. If I'm talking about the Krakatoa eruption, so Krakatoa eruption happened in the late 1880s. So Krakatoa eruption, it is said that it basically resulted in such a high eruption of magma, such a high eruption of sulfurous gases, that entire earth was covered by volcanic ash, by volcanic dust, by close to 3 days, and entire globe basically had a very less receipt of sun's insolation. Now, in place of the Krakatoa, we are having his son. So, the son of Krakatoa, it is referred to as Anak Krakatoa. So, this is near the Indonesian island of Bali. And in 2017 and 18, his son also erupted. So, like father, like son. So, this is Anak Krakatoa, the son of Krakatoa. So, it erupted with such great ferocity that the land on its western shore, it completely subsided into the ocean, creating a very unique phenomenon called as volcanic tsunami. So the tourists which were actually enjoying these locations, they did not expect tsunami coming because of a volcanic eruption. So this can be asked as a case study for each and every one of you. So please take note of this, that Anak Krakatoa is associated with volcanic tsunami. Okay, sir. So these are basically your 4 types of classification on the basis of intensity of eruption. But yet still, we are not able to figure out, sir, how can we basically understand the distribution of volcanoes? So to understand this, we should first try to basically understand the classification of volcanoes on the basis of type of central vent, because this will give us a clear idea as to how we can actually classify everything. So if I'm talking about the types of volcano on the basis of central vent, so here we can have 2 types of central vent. Either we can have cylindrical vent. So vent in the sense that the volcanic conduit in the sense that from where is your magma actually erupting, the shape of the vent, whether is it cylindrical or is it fissure type. Fissure type means you are having numerous small openings. So here again, if you are having cylindrical type of vent, and in the cylindrical type of vent, if you are having andesitic / rhyolitic magma coming, so you can have the formation of such volcanoes which are basically unique to Earth. Unique to Earth in the sense, I'm talking about continents, I'm not talking about the oceans. We do have the world's tallest volcano, world's in the sense, if I'm talking about the world's tallest volcano, it is in South America, Ojos del Salado, but the tallest peak in the solar system is on Mars. It is referred to as Mount Olympus. It is a kind of stratovolcano itself. So if you are having andesitic or rhyolitic eruptions, you are having layers of volcanic magma coming together. So the layers of volcanic magma, they will solidify, they will accrete, creating volcano of accumulation. So such volcanoes, they are referred to as stratovolcanoes, or you can call them as cylindrical conical peaks. So they will be basically unique to continents, because if I'm talking about the ocean floor, the eruptions on the oceanic floor will be predominantly basaltic eruptions. So basaltic eruptions cannot create such high elevations. They will be predominantly creating the mid-oceanic ridges per se. So if I'm trying to decode that where do we find stratovolcanoes, stratovolcanoes will be predominantly found on the continents. They will be referred to as the layers of volcanic magma associated. So if I'm trying to discuss with you all, sir, what are some of the good examples of stratovolcanoes? So let me mark it up for all of you on the atlas so that all of you can appreciate it. Sir, where do we have? So some of the recent examples also I will give you, which will help you in your mains answer writing. So in North America, you are having at the border of Alaska and at the border of Canada, you are having basically two volcanic peaks. You have Mount Logan and you have Mount St. Elias. So you have Mount Logan and you have Mount St. Elias. At the border of Canada and USA near Seattle, you have Mount Rainier. Then below in the Cascade Range and the Coast Range, you have Mount Whitney, and then you have Mount Shasta. So Mount Whitney, Mount Shasta in the Bay region, San Francisco, the Silicon Valley. Then two very active volcanoes of Mexico. They are very much in news, so you need to remember these. So two very active volcanoes of Mexico. You have Coapa, Cate, Petal, and on the eastern side you are having a volcano called as Pico de Orizaba. You are having Pico de Orizaba. Two very active volcanoes in Mexico. You have Western Sierra Madre, Eastern Sierra Madre. So you are having this. In South America, two very active volcanoes near equator. So you have Mount Cotopaxi, and then you are having Mount Chimborazo. So two very active volcanoes near the equator. Then to the south of Atacama, you find the world's tallest volcano, which is referred to as Ojos del Salado. Near Lake Titicaca, you also have a very important volcanic peak. You have Mount Ilampu. So if I'm just showcasing you basically how does Ojos del Salado look like. So the tallest volcanic peak that we have. So basically this is how you are having Ojos del Salado, the world's tallest volcanic peak that we have on earth. So height is more than 6,000 meters. So I guess like this peak basically surmounts the elevation of majority of the fold mountains that we have on earth per se. Yeah. So this is basically your Ojos del Salado. In Italy, in this region, we have Stromboli, we have Mount Sicily, we have Mount Etna. So Mount Etna, it is in the island of Sicily. So Mount Etna erupted last week itself. Last week you are having the eruption of Etna. You have Mount Etna in Sicily, then you have Mount Vesuvius, Mount Stromboli. In Africa, you are having three mountains. You are having the tallest peak of Africa, you have Mount Kilimanjaro. Then you have Mount Margarita, Mount Kenya. In India, the only active volcano that we have, it is referred to as the Byron Island volcano. And the tallest volcano, the most active volcano in Japan, in the sense of that it can erupt anytime, you are having Mount Fujisan or Mount Fuji, at the foothills of which we are having Tokyo, the world's most populated city and also the world's most biggest city. Then Southwest Pacific, you are having numerous volcanoes. We don't need to remember that. So even if you remember these many examples, it will be very much convenient for all of you to frame the answers per se in the mains. So these are basically your volcanoes created because of what? Volcanoes created because of andesitic eruptions in central vent. But if you are having central vent and you are having basaltic eruptions, so basaltic magma, as you all know, that it has the tendency to actually spread. So in cylindrical vent, if you are having basaltic magma which is spreading, it can create what? It can create shield domes. So domal mountains. The most prominent example of this, the world's tallest peak, Mauna Kea and Mauna Loa. So if I'm just showcasing you the world's tallest peak, sir, how does Mauna Kea and Mauna Kea look like? Mauna Kea and Mauna Loa. So these are your world's tallest peaks. If you carefully observe, how does Mauna Kea look like? So Mauna Kea will look like a domal shield. You see this? Why? Because of basically the basaltic eruption. So it is just like a common domal highland per se. 4,000 meters above sea level, 6,000 meters below sea level. So combined height more than 10,000 meters. That is why the tallest peak on earth per se. And now last but not the least, if you are having numerous fissures in the sense that in the ground you are having small cracks, and from this small cracks, if you are having eruption of ultramafic basaltic magma which is coming from the mantle core boundary, so you can have creation of what, guys? You can have creation of extensive lava plateaus. They're extensive lava plateaus in the sense of what? So let us try to understand. So extensive lava plateaus in the sense of the hotspot based eruption. So in North America, you are having the Yellowstone Yosemite hotspot, which has created what? Which has created basically the Columbia Snake River Plateau. Sir, you are having the hotspot eruptions of the South Sandwich Island, which have actually created your Patagonia region of South America. Then the Indian plate, when it was traversing over the Mauritius Reunion hotspot, so the Mauritius Reunion hotspot has created the Deccan lava plateau. It has created the Deccan traps with its very high clay content. So very difficult to recharge the groundwater once it is extracted. The soil is almost basically impermeable. That is why you will see Gujarat, Maharashtra, the region from where I am taking this lecture, Vidarbha, Marathwada, Gir region, the Saurashtra region. This is where you will be seeing highest number of farmer suicides. Why? Because the Deccan traps, they are not good reservoirs of groundwater. And in this, we are actually cultivating sugarcane. So it becomes very daunting that you are actually cultivating water guzzling crops like sugarcane. You are cultivating water guzzling crops like cotton in such areas which are having less groundwater reserve. This is not done. And then we basically have a very important province of Western Australia called as Kimberley. So here you are having Kerguelen hotspot. It has actually created Kimberley, the Western Australian plateau region, and the Kerguelen hotspot, which is to the north of Antarctica. It has also created the 90-degree east ridge, and it has also created the Ladakh province and the richest mineral region that we have in India, the Chota Nagpur region in Jharkhand, Hazaribagh plateau and Ranchi plateau. So whenever you will be having small fissures opening, so small features, they can create extensive lava plateaus. This is very important, guys. So now that we have understood the types of volcanoes, let us try to understand, sir, where we can have the distribution of volcanoes. So, but naturally, if I'm talking about the distribution of volcanoes, the first type of distribution can happen over where? So the first type of distribution can happen over the more locations. There are more locations in the sense where you are having the formation of mid-oceanic ridges. So all of us know that if I'm talking about the mid-oceanic ridges of the Atlantic, so you are having Dolphin Ridge, Challenger Ridge, the mid-oceanic ridge of the Pacific. This is active. The mid-oceanic ridge of the Indian Ocean is completely passive. You don't have any active ridge system in the Indian Ocean. The ridge system of the Pacific and the Atlantic is only active. So the first kind of volcanic distribution we can have is actually the more locations, the Atlantic more stretching for more than 80,000 kilometers. And on the Atlantic more, you can have numerous such locations where the more is actually exposed. Like we have Iceland. So Iceland, as you all know, like last month, more than 2,000 eruptions a single day, 2,000 small earthquakes a single day. It's basically exposed more of the Atlantic. So you can actually see the North American plate and the Eurasian plate splitting. Then you can have Azores Island. Then we can have Assumption. Then we can have Saint Helena on the west side of Africa in the middle of Atlantic, where Napoleon Bonaparte was kept for life imprisonment after the defeat at Battle of Waterloo. Then we have Tristan da Cunha. So Tristan da Cunha, the loneliest island in the world per se. Close to 300 people live, but it takes 7 days to go over here from the African mainland because the only option is by sheep. So these are some of the islands which are on the Atlantic more, which can be associated with divergent boundary plate tectonics and also basaltic eruptions. But the majority of the eruptions, the majority of the volcanoes will be distributed where? So the majority of the volcanoes will be distributed along the Pacific Ring of Fire, PROF. Why, sir? Because along the Pacific Ring of Fire, you are going to have subduction margins. Sir, subduction margins in the sense of what? That if I'm talking about the Pacific Ocean, the Pacific Ocean is having subduction margins on the west, on the east, and so west, then you are having east, and then you are having north. So combine this belt, you are having subduction margins. So whenever you will be having subduction margins, but naturally you are going to have what? But naturally you will be having the associated volcanism, the associated earthquakes. So staggering 85% of the volcanic eruptions that we have on Earth, it is in the Pacific Ring of Fire. Sir, right now the Great African Rift Valley has also become active. So the African plate, namely the Nubian plate and the Somali plate, they are now drifting apart from each other. So you are actually having the formation of a new divergent boundary on the east side of Africa per se. So this is also very, very important. And then if we are trying to understand, sir, where else can we have the distribution of earthquakes? So we can have the distribution of earthquakes along Mars. We can have the distribution of earthquakes along the PROF, Pacific Ring of Fire, but we can also have isolated hotspots. Isolated hotspots means they are not a part of any Mars system. So we have the Hawaiian hotspot. We have the Galapagos hotspot on the west coast of South America, ruled by Ecuador. So Galapagos is where Charles Darwin conducted his experiments and gave his theory of evolution. Then we can have Kerguelen hotspot. We can also have Mauritius Reunion hotspot. So isolated hotspot, the PROF region, and the divergent boundaries along the mall. These are basically briefly the three distribution of volcanism that we have on Earth. But sir, volcanism alone is not going to do for us. So we need to understand basically the earthquakes in detail too, because this is from where we will be able to justify and answer the questions that we have. So now let us try to understand, sir, what are basically earthquakes, and if we are trying to paint this topic from Mains perspective, how can we understand this? So in a nutshell, if I'm talking about earthquakes, so how can we define earthquake, guys? So in a nutshell, we can define the earthquakes as basically rigorous shaking of ground. Rigorous shaking of ground. Why, sir? We'll just figure it out. You all know that it is because of seismic waves, namely the R wave and the L wave. So the vigorous shaking of ground can be either natural or it can be man-made. Sir, natural in sense of what? Sir, natural in sense of mantle dynamics. So basically you are having the lithospheric plates either moving apart from each other, moving into each other, or just slipping past each other. So divergent, convergent, and transform boundaries predominantly. Or we can also have the earthquakes because of man-made activities. Man-made activities in the sense of what? Sir, in sense of large-scale drilling and mining. Sir, we can have because of nuclear tests also, definitely. Thank God we did not have a nuclear war. Otherwise, 1 month back we were just here. And we can also have because of faulty construction of dams. This is referred to as reservoir induced seismicity. We refer to it as RIS. So if you have ever seen a dam collapsing, so the dam will never collapse from above. The dam will always collapse from below. Why? Because if the base of the dam is not wide, the water percolates in, the water seeps in, and it starts applying hydrostatic pressure. That is why the entire dam wall collapses. So this is referred to as reservoir induced seismicity, which did happen in Maharashtra. You are having the Konya Dam, wherein you are having Shivaji Sagar Reservoir. So you had an earthquake near Latur coming because of this. But if I'm talking about earthquakes, so man-made earthquakes, they are not of that great intensity. Only exception being the nuclear test. So we have to focus on where we have to focus on the natural earthquakes that we have. So now let us try to understand what are the factors responsible for the natural earthquakes. If I'm talking about natural earthquake, guys, so they are basically the consequence of vigorous shaking of ground. The shaking of ground because of what? The shaking of ground because of two transverse waves. Transverse wave meaning what? That the direction of the motion or the direction of the vibration of the particles of the medium is perpendicular to the energy flow. So let's say this is a medium, the wire of this mic is a medium, and if basically you are having the passage of energy like this, so the energy is flowing like this, but the particles of the medium, they are vibrating perpendicular to the direction of energy flow. Kind of a harmonic motion, kind of a guitar string plug. So these are referred to as transverse waves. So when the P waves and the S waves, they reach the surface. So from the focus, the energy is reaching the surface, it is reaching the epicenter. And from the epicenter, the energy is getting distributed on the Earth's surface. So the distribution of energy that occurs, it occurs in the form of L wave, love wave, and it occurs on the basis of R wave. We also refer to it as Rayleigh wave. Remember, both of these waves are transverse waves. Now, if I'm talking about love wave, what happens in love wave, guys? Sir, in love wave, you are having the horizontal motion or the horizontal wobbling of the particles of the medium. So let's say a wave is moving like this. So the particles of the medium, they will start moving perpendicularly in horizontal direction with respect to the energy flow. So let's say if a building is standing like this and the L wave is passing through this building, so this building will start to wobble. And this is where the foundation of the building, if it's not strong, entire building collapses. So the love wave is responsible for the wobbling of the buildings, and then we are also having Rayleigh wave. So in Rayleigh wave, what will happen? Sir, in Rayleigh wave, you will be basically having the curling of ground. So if you are having a medium and if Rayleigh wave is passing through it, the ground gets curled up and the ground uplifts a little bit. So you must have seen during the earthquakes that the ground gets curled up and it rises. So this is because of passage of R wave. Now, if we are trying to understand that how can we have basically the types of earthquakes. So the types of earthquakes that we have, they are predominantly three types. So we are having shallow focus earthquakes, we are having intermediary focus earthquake, and then we are having deep focus earthquake. So shallow focus in the sense that from how much depth is the earthquake actually originating. If I'm talking about shallow focus earthquake, guys, so in shallow focus earthquake, the energy comes from roughly 30 kilometers beneath the surface. So the shallow focus earthquake can be associated with any type of boundary. Divergent boundary, but naturally, sir, convergent boundary also. So you can have the trench locations where the plate is actually sinking, the plate is actually subducting, and you can also have the transform boundary or the transform faults. Definitely, sir. So even if you are having the upliftment of mountains like the Himalayas because of the underthrusting of the Indian plate beneath the Eurasian plate, you can have shallow focus earthquakes. So shallow focus earthquakes are universal, means they can be found in every type of plate boundary interaction. And that is why, guys, they also become the most deadly. Why? Because the energy is coming just beneath the surface. So the energy comes with full intensity. So typically it has been found that even though the shallow focus earthquakes carry less energy than the intermediary focus and a deep focus earthquake, but because they are originating at a lesser depth compared to intermediary focus and deep focus, they often become the deadliest of all these. This is very important. Then if I'm talking about intermediary focus, so intermediary focus in the sense that the energy is coming roughly 300 kilometers below the surface, and then we are having deep focus earthquakes wherein the energy is coming roughly 500 to 700 kilometers beneath the surface. So now this is a very important current affairs, guys. Those of you who are watching this lecture live, please understand this. This zone is very important. So this is referred to as the Benioff-Wadati zone. One such zone has been discovered in the Eastern Pacific. Let us try to understand, sir, what is this Benioff-Wadati zone? So if I'm talking about Benioff-Wadati zone, a very important current affair for 2025. So Benioff-Wadati zone in the sense that, let's say you are having Philippines plate and let's say this is your Pacific plate. Let's assume this is your Pacific plate and let us assume this is your Philippines plate, right? So you are having the Philippines trench or you are having the Mariana trench. So now the region where the Pacific plate is subducting and the Pacific plate is entering into the mantle. So as the Pacific plate descends, it breaks and it enters into the mantle. So you can imagine if the plate is entering into the mantle, how huge must be the frictional forces, because as you descend into the mantle, the density rises to up to 5 to 7 specific density, which is given with respect to water. So you are moving into high density region. So but naturally some part of this plate is going to break, it is going to enter into the mantle, and some part of it will melt and it will rise up, creating long linear chain of volcanic archipelagos like Philippines, Japan, Kuril. So these are all your volcanic archipelagos. So the region where one part of the plate breaks, it descends, it enters into the mantle, and one part of it can rise up to create long linear chain of volcanic archipelagos. So this region is referred to as the Benioff-Wadati zone, which is predominantly associated with what? Which is predominantly associated only with the subduction margins. Very, very important. Here, if I'm talking about, sir, what are the predominant minerals that we find? So the predominant minerals that we find, they are basically all the unstable forms of olivine. So olivine, the dominant mineral of the upper mantle. So olivine itself is very much unstable. So olivine converts into progressively unstable forms like perovskite, like garnet and spinel, which are very, very reactive. And that is why intermediary focus and deep focus earthquakes are associated with Benioff-Wadati zone. And hence, if I'm talking about Japan per se, if I'm taking you to the east of Japan, so Japan basically sits at the confluence of 4 plate boundaries: the Philippines plate, the Pacific plate, the Amur plate and the Okhotsk plate. 4 plate boundaries Japan is sitting, and you are actually having subduction margins. So, but naturally Japan is going to have very high intensity of earthquakes, right? Definitely. So this is basically your Benioff-Wadati zone. Very, very important current affairs for this year's mains, guys. Please try to understand and appreciate this. So now, as we have understood the earthquakes, but we have to understand what is happening in India, and we need to understand what is happening in Turkey, because close to 43,000 people died. The same thing happened in Myanmar, the Sangin fault. So for that, we need to understand the process of rifting and faulting. So rifting and faulting will result into formation of block mountain. So let us add little bit icing on our cake. Let us also discuss quickly the mountains that we have, because this will be a good revision for each and every one of you, and you will be able to figure out, sir, how to capitalize on this, how to use on this. If I'm talking about mountains, so but naturally we have volcanic mountains. So volcanic mountains I just illustrated for each and every one of you. We have the stratovo mountains, we have the shields, we have the cones. If I'm talking about the true mountains or the true orogens that we have, so they are referred to as basically the fold mountains. So fold mountains, basically they will be unique to Earth. Nowhere in the solar system you will be finding fold mountains except Earth. and they are the consequence of CC type of collision per se. So if I'm talking about fold mountains, guys, what can be its associated features? Like, let's say if I'm talking about Himalayas, do Himalayas exist as one single mountain range? No. We are having Great Himalayas, we are having Middle Himalayas, we are having Shivaliks. We also have the Trans Himalayas, Karakoram, Ladakh, Kailash, Jhanskar. We also have Purvanchal, Bareil Range. Sorry, we have the Patkai Boom, Naga Hills, Mizo Hills, Manipur Hills, Lushai Mountains, Blue Mountains. So fold mountains have three very unique characteristics. One of them was asked in basically this year's prelims also, that where do we have the Andes? Which countries do the Andes pass through? So Andes, you are having Cordilleras, Eastern Cordillera, Western Cordillera, Central Cordillera. So the three unique features that we have is that the fold mountains, they will always exist as series of parallel ranges. They will never exist in isolation. Then second feature, they will be always carrying sedimentary rocks of marine origin. Why? Because the CC collision, that is the last stage of collision, prior to it the boundary was OC, prior to it the boundary was OO. So actually your sea floor itself is uplifting into the fold mountains. So if I'm talking about Himalayas, they are nothing but the uplifted Tethyan folds. They are uplifted Tethyan accretionary prism. It is as simple as this. Your Tethys sea floor has uplifted into the tallest elevations on earth, namely the Himalayas. So that is why the universal rock of all the fold mountains is limestone, calcium carbonate. And fold mountains, they will never be randomly formed. They will always be found alongside the plate boundaries. They will always be found alongside the plate margins. So if this is Eurasian plate, this is the Indian plate, the steacher, the zone of stitching, the zone of basically steacher is where you are having the formation of Himalaya. Okay, sir. Then we can have escarpments. Escarpments meaning the edges of a plateau. So if you are able to see my face, so you are able to see the side face. This is the side angle of my face. So this is referred to as the escarpment or the edge of my face. So if you observe the Deccan lava plateau, and if you see the Deccan lava plateau from the Arabian Sea side, you will be able to see the Western Ghats. You will be able to see the Sahyadris. So Sahyadris, they are nothing but the escarpment or the edges of the Deccan lava plateau. Similarly, we'll find in Australia, Kimberley, Hammersley, Darling, Musgrave, then you are having McDonald Range. All of these, they are the edges of the Western Australian plateau. It is as simple as this. Then we can have residual/relict mountains. Residual/relict mountains means what, guys? Residual/relict mountains meaning such mountains, when they formed, they were very high in elevation, like Aravalis, Vindhyas, Satpuras. They are all very ancient Archean fold mountains. They have uplifted close to 3 billion years ago. Just imagine when they uplifted, how much high their elevation must be, right? But today, because of erosion, today because of denudation, today because of standing the test of the time, they today basically remain as what? They basically remain as residual/relict mountains. The average elevation less than 600 meters. But the most important one, they are basically the block mountains. Why? Because they are the consequence of rifting and faulting. So everybody try to understand this process of rifting and faulting, because I am guessing that this year this can be the question which can be framed in mains. And remember, the diagrams are very important. So after this lecture, I will urge each and every one of you to again revisit this lecture, pause the lecture and try to incorporate these diagrams in your notes, because then you will be able to understand this process even better. So now let us try to understand the process of rifting and faulting that we have. So actually the name should not be rifting and faulting, the name should be faulting and rifting. So faulting and rifting in the sense that you are having cracks developing in the crust and you are having the eventual or the resultant displacement of the entire crust in totality. This word is very important. The eventual displacement, the eventual rifting of the crust in totality. So your entire continental crust is cracking, it is rifting for roughly 60 to 80 kilometers in depth, the entire depth. This is very important. If I'm talking about faulting and rifting, we need to consider basically two possibilities. That the first possibility is that the forces which are acting on the crust, they are actually displaced. Actually displaced in the sense that if we are having one block, so one force is acting like this, one force is acting like this. The two forces are not acting along the same line, the two forces are acting actually displaced. So in such a case, if the two forces are actually displaced, if this is F1 and if this is F2, the crack which is developed, it is found that it is always vertical. The crack is always straight, and the eventual rifting happens in such a way that, let's say if you are having point A and point B. So if with respect to point B, point A rifts towards the right. If it slips towards the right, we call it as right slip fault or we call it as dextral fault. And with respect to point B, if point A is rifting towards the left, we call it as left slip fault or we refer to it as sinistral fault. And the relative displacement in the sense that with respect to point B, how much point A has actually displaced either in left or right, we refer to it as heave. So heave is nothing but the relative displacement as a result of rifting. So such kind of rifting or such kind of faulting, it is also referred to as transform fault. We also refer to it as wrench fault or shear fault. The most common example of this is of course going to be moor location, which are all actually displaced. So if I'm just showcasing you, sir, how are the moors actually displaced? So let us try to understand it through map. Now, those of you who are watching my lecture live or those of you who will watch my lecture in recorded format, if you are able to see this image, guys, so you are consider yourself very lucky, because this kind of analysis can only be given in an online medium. It's very difficult to teach each and everything of this which I'm showcasing on the screen in offline format. You're all very fortunate enough, because back in our days we do not have this luxury, right? So if you see, this is your Atlantic moor and you can see numerous cracks basically forming over here. Sir, we are having a huge crack over here. Sir, what is this? So this is referred to as the San Andreas fault. So San Andreas fault meaning that you are having a small microplate. It is called as Juan de Fuca plate. So Juan de Fuca plate is moving southwards and the North American plate is moving northwards. So you are having transform fault, the shear slash tear fault. You are having creation of San Andreas fault, and in the Atlantic moor, because of differential rates of spreading, the mantle convection limbs below, sometimes they are basically stretching the crust either towards the right more or towards the left more. That is why you are having numerous transform faults happening where? Happening basically alongside the Atlantic moor. Very, very important. Then, sir, this case is not that much what I can say applied case, because this is typically not found on the continent. So sir, which case is typically normally found on the continent? So this is very important, and once I showcase you the image of this, you will attain enlightenment. You will get the Paramanand, which we say that, oh sir, now every concept is clear and everything is there in our brain. So now let us try to understand case B, where the forces are acting along the same line. Sir, acting along the same line in the sense that if this is the block, so both of the forces, they are acting along the same axis. So you can have the tangential forces of compression or basically the tension. So you can either have the crust being stretched or you can have the crust being compressed. So let us consider the first case where the forces acting are compressive. So in such a case, the crack which is developed, it is always inclined with respect to the vertical. The crack will never be straight, it will always be inclined. You can very well understand, because when the forces are acting along the same line, we really don't know which part of the crust is going to yield first. So as the crack develops, the area beneath the crack, it is referred to as footwall. The area above the crack is referred to as hanging wall. So it is basically found that whenever the forces are compressive, as a rule, the hanging walls are thrown up, and as a rule, the footwalls are thrown below. So the hanging walls are thrown up and the footwalls are basically thrown below. This is found as a rule per se. So if the hanging walls are thrown up and the footwalls are thrown below, this process is referred to as what? This process is referred to as compressive rifting and reverse faulting. Why? Because ideally speaking, your hanging walls should be thrown below. Hanging walls should carry less weight, they should be thrown below, and your footwall should be elevated. But in reality, what we are trying to find is that the hanging walls will be elevated and sir, the footwalls are thrown below. So because of this, what is going to happen is that such kind of rifting is referred to as compressive rifting and reverse faulting. So we can very well understand that in the world, we can have such kind of incidences happening where, sir, very close to our home in the Himalayas, because in the Himalayas you are having intense compression. So Himalayas will be going to have series of reverse faults, series of reverse faults. You have main central thrust, you have main boundary fault, and then you are going to have your Himalayan front fault. But now, what is commonly found in nature? Sir, the forces which are found are tensile. What is happening in Africa right now? So beneath the Africa, you are having the splitting up of Nubian plate and you are having the splitting up of Somali plate. So African plate and the Somali plate, they are basically splitting apart from each other. So as they are splitting apart from each other, so below you are having a mantle convection limb which is tensile in nature. So if you are having the tangential forces which are basically tensile in nature, so here now what happens is that here the footwalls are thrown up and the hanging walls are thrown below. So let's say a crack has developed, the area above the crack is hanging wall, the area below the crack is a footwall. So whenever we are having the tensile forces acting, so the footwalls will be thrown above and the hanging walls will be thrown below. So let us try to understand it through a very common example. So let's say you are having a block like this. Let's say you are having the formation of a divergent boundary, sir. Below it, you are having a mantle convection limb, which is actually splitting up the block per se. So what we can understand is, sir, the area beneath the crack is footwall, the area above the crack, it is hanging wall. So sir, in tensile rifting, what is thrown above and what is thrown below? Sir, the footwall is thrown above and the hanging wall is thrown below. And that is why such kind of rifting and faulting is referred to as what? This is referred to as tensile rifting and normal faulting. Why we call it as normal faulting? Because this is typically found in the nature. So the block which gets thrown above, we call it as horst. And sir, the block which gets thrown below, we call it as graben. So the horst can form the block mountain and the graben can form the rift valley. For example, the Great African Rift Valley. For example, your Narmada rifts. So if I just showcase you the image, that how does the Narmada rift look like? So this is how your Narmada rift looks like. So just one example and everything will be clear to you. See, this is the beauty of geography, guys, that whatever I'm teaching you, I'm able to basically showcase you through actual images, actual photos. So see, this is your Vindhyas range, this is your Satpura range. So your footwalls are elevated and sir, your hanging wall has gone down. So this is referred to as the Narmada Rift Valley. Beda Ghat, The shooting location of Donkey movie, Mohenjo-daro movie. So very, very useful. In nature, therefore, we find what, sir? In nature, therefore, this is the common case which is found, sir, tensile rifting and normal faulting. So now if I'm trying to understand the distribution of earthquakes, where do we have? So, but naturally, sir, the first distribution of earthquake which can be have, of course, it is going to be in the Prof region, the Pacific Ring of Fire. Why Pacific Ring of Fire? Because almost all the margins are active. You are having divergent boundary, you are having convergent boundary. Sir, in Pacific region, do we have divergent boundary? The answer is both yes or no. On the east side towards the southeast, you do have the divergent boundary, but it is not of that consequence. Predominantly, you are having OC and OO convergence boundary associated with pure subduction, and whenever we will be having subduction margins, they will be always associated with andesitic eruptions, and that is why over here we are having shallow focus, intermediate focus and deep focus. So that is why the Pacific Ring of Fire, guys, becomes seismically the most active belt on earth. Why? Because here we have all three types of earthquakes: shallow focus, intermediate focus and deep focus. Then next, 10% of the earthquakes, they are typically found where? They are typically found in the alpine belt. Alpine belt meaning the Trans-Eurasian belt, which starts from the Iberian Peninsula of Spain. It moves through Alps, it enters into Turkey, Taurus Mountains, Greece, Pindus Mountains. Then you come towards the Iranian mountains of Zagros, Elbrus. Then you have Afghanistan, Hindu Kush, Pamir, Pakistan, Suleiman and Kirthar, India, Himalaya, which extends into Myanmar as Arkan Yoma and Pegu Yoma. So basically, if I'm talking about the distribution of earthquakes, so the distribution of earthquakes will be basically where the distribution of earthquakes, close to 10% of the earthquakes will be in the alpine belt. Very, 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 very important. So apart from the alpine belt, we can also have earthquakes being found where? Sir, we can find the earthquake belts in the transform boundaries too. The transform boundaries in the sense that where you are having slipping up of plates. So we are having the Juan de Fuca and the North American plate, they are just slipping past each other. So as they are slipping past each other, so we can have the transform boundaries which can have the associated earthquakes. And then last but not the least, we can have earthquakes where, which are basically randomly distributed. Randomly distributed in the sense of what? That certain earthquakes, they can occur along the hotspots, but you can very well understand if we are having very old landmass in the sense that if we are basically having a landmass like India, so all of us know that the origin of India is close to 3 billion years. India was basically a part of Antarctica, and Antarctica, where we are having the Gondwana land, India broke up from Gondwana land close to 100 to 120 million years ago, and then basically India started its northward journey. So just imagine that when you were small, when you were a kid, you basically fell from a bicycle. So you developed a hairline crack in your bone, right? So you developed a hairline crack in your bone. You did not give enough care, you did not provide enough care to the hairline crack, and when you basically grew up, when you become an adult and you again fell on the same spot, that crack basically ruptured. So same thing is happening where? Same thing is happening, sir, in India. Same thing happened where, sir? In Myanmar. Same thing happened where, sir? In Turkey. Why? Because the ancient faults, they got reactivated because of intense compression. So we can have basically the ancient faults which can get reactivated. Like in Gujarat, we have the Alaban fault, the Bhuj earthquake. And now if I'm trying to give you a good analysis, this question can come in this year's mains. So try to understand this part very, very carefully. That why if I'm talking about Turkey, why if I'm talking about Myanmar, why if I'm talking about Himalaya, so Kathmandu, Turkey, India, Myanmar, sir, why do we have such a heavy loss of life? Why there are so much casualties over here? So if I'm talking about alpine belt, here predominantly the collision is CC type. You are having basically two plates colliding with each other. So as two plates basically collide with each other, but naturally you are going to have very intense seismicity. Sir, if you are having two plates colliding, but naturally you are going to have what? But naturally you are going to have series of reverse faults. But if I'm talking about the alpine belt, so in the alpine belt you find a very special type of fault. What is this special type of fault called as? So this special type of fault is called as oblique fault. Oblique fault in the sense of what? That here not only you have horizontal displacement, but along with horizontal displacement you also have vertical displacement. So the foot walls do get elevated, the hanging walls do go down, but along with it basically you also have what? Along with it you also have vertical and horizontal displacement both acting together. And that is why if you are having a structure of a building which is typically found in India, right? If you go to in any India's commercial complex, so you basically are having what? Sir, in any commercial complex, beneath you are having shops and above you are having residential complexes, you are having residential flats. So if the earthquake comes, if the L wave starts wobbling the ground, if the L wave starts shaking the ground, sir, do we have adequate beam and column support to support the entire structure above? The answer is no. So soft storage structure in the sense that where on the ground floors you do not have adequate beam and column support, and above whichever structure you have, the entire structure collapses like a cake. So this is actually referred to as what? This is actually referred to as pancake collapse. And this is the main reason that we have maximum casualty, maximum loss of life, in particular the South Asian region. So if I just showcase you the Myanmar earthquake, like what actually happened in Myanmar. So in Myanmar earthquake, you basically had what? So see the images of the building. So this is referred to as what, guys? This is referred to as pancake collapse. If you carefully observe, the shops below, they have given up, whereas the residential complex above is still intact. Why so? Because the building in the ground floor was not having what? Was not having adequate beam and column support. So as it was not having adequate beam and column support, that is why basically the entire building collapsed. So now this can be asked in this year's mains as to why is this happening? So this is happening because of what? This is basically happening because we do not have adequate earthquake norms. We do not retrofit the buildings with adequate materials. So if we are trying to understand, sir, which country in the world does this the best? So you are basically having the Japanese building code. Use this as your main cherry points. This is very, very important, guys. So focus on the screen and try to understand and appreciate this. So the Japanese building code is very strict. So you are having three types of structure in the Japanese building code, and one of it is now compulsory. If I'm just showcasing you at what is basically the Japanese building code and how it basically translates into retrofitting of the buildings. So you have basically three types. You have Taishin structure, you have Shaishin structure, and you have Menshin structure. So Taishin, Saishin, and Menshin. So Taishin, Saishin, and Menshin in the sense that in Taishin structure, we basically use high strength materials. So we basically use high strength steel, so that as the building it starts to wobble, the structure is not losing its integrity. So this is referred to as Taishin structure. Then we are having Shaishin structure. And in Shaishin structure, what do we have? So in Shaishin structure, you basically use damper. So damper in the sense that in the middle of buildings or in the side walls, you are basically placing very high strength steel block or concrete block. So even if the building starts to wobble, the center of gravity of the building is not displaced. But today, the most acceptable solution to basically the retrofitting of earthquakes, it is referred to as what? It is referred to as Manchin structure. So in Manchin structure, we have base isolation. So the foundation of the building itself is decoupled. Foundation of the building is decoupled in the sense of what? That as we have in our cars, so between the tires and the body, you are having shock ups. So even if the tires, they basically wobble, the body's integrity is not lost. So you are basically adding shock absorbers to the building. So this is referred to as what, guys? This is referred to as the Manchin structure. Taishin, Manchin and Shaishin. So this can be a very good basically analysis of the earthquakes, wherein in the high risk zones of India. So if you understand that which regions in India are most prone to earthquakes. So let me just open up the map of India, wherein we can discuss which are the high risk zones that we have. So this is basically the earthquake seismicity map of India. So the earthquake seismicity map, wherein we are having the highest seismicity. So if you see the Great Himalayan Belt, the Great Himalayan Belt is where we are having zone 5 and zone 4. So this belt is very active. Why? Because we are having CC boundaries. So here, if we look after basically the strength of the buildings, and if we try to incorporate appropriate building norms, we can control the loss of casualty and life. High seismicity is also in Bhuj, it is also in Western Ghats. Whereas in the tectonically stable regions like zone 2 and zone 3, we did not worry about the earthquake retrofitting, but high risk zones of India should include this. This is very, 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 very important. Okay. So here I finish off with the first segment in important geophysical phenomenon like earthquakes and volcanism. So now I'll be taking up 10 minutes of break, and after that I'll be starting off with a very important topic called as cyclones, because cyclones is a very, very important topic, and I will be discussing both temperate cyclones as well as tropical cyclones with all of you, and then we will end up our lecture using coral reefs. So another 1 hour to go. So it's 8:20 to be not that much approximate, it's 8:18. So we'll meet again at 8:30. So 8:30 we'll resume the lectures again, and we'll be doing cyclones, the temperate cyclones, the tropical cyclones. We'll understand the associated current affairs, and we'll try to understand what is coral reef bleaching. So very, very important. So 8:30 we are taking a break, and 8:30 we'll resume the again. Okay, thank you everybody. Hello. Okay guys, we are back. So now I'm starting off a very important topic which on a scale of 1 to 10 has scored almost 9 or 10 in terms of the probability of being asked in civil services examination, and dare I say across all the examinations which are conducted by respective public state service commissions out there. So we are going to understand a topic called as cyclone in detail, because this is very important, and please make sure that you understand this topic from a very great conceptual clarity perspective, because whatever information I am going to give you on this board, especially those of you who are going to give this year's mains, this information is very much sacrosanct. So my research goes into all the textbook, my research goes into all the research papers out there, and based on that I'm giving you all of this information. So you are going to get a very crisp and a very concise information of this topic. So try to focus on this topic with full clarity, with utmost attention. Okay. If I'm talking about cyclones per se, so what cyclones actually are? So cyclones, they are nothing but localized low pressure core system. Localized low pressure core systems in the sense that you are having a low pressure. So surrounding this low pressure, the pressure is continuously falling from all the directions. In the sense of what, sir? That if you are trying to factor in, sir, how much is the pressure in the surrounding areas, so we'll see that from the surrounding areas, the pressure is falling from all the direction towards the center. Meaning that, sir, the pressure gradient is continuously falling towards it. The change of pressure is basically continuously happening towards the center. So let's say if we are having a cyclone which is being formed, so cyclone is represented by closed circular isobars. So let's say that the outermost isobar is conforming to 1100 millibar. Let's say the isobar above or ahead of it, it is 1050 millibar. So the pressure is falling by close to 50 millibar as we are moving towards this low pressure core. And this low pressure core, let's say we are having 950 millibars of pressure. So now what is going to happen? As we all know that low pressure is nothing but area of convergence. Convergence in the sense that low pressure is going to attract winds from every direction. So because of this, the winds, they converge towards it. And as the winds, they start converging towards it, what is going to happen is that they will start to spiral. Sir, why they will start to spiral? Because we are having Coriolis force. So because of Coriolis force, the winds will start spiraling towards the center, towards right if you are in the northern hemisphere, and towards left if you are in the southern hemisphere. So if we are trying to understand and appreciate, sir, what will be the direction of spiraling of the cyclones in the northern hemisphere versus the spiraling of cyclones in the southern hemisphere. So let's say I'm talking about the northern hemisphere first. So this is your low pressure core and this is your cyclone. So in the northern hemisphere, the Coriolis force deflection is towards the right. So as the winds basically come towards the center, they are deflecting towards the right and then they are spiraling. The wind, they are deflecting towards their right and then spiraling towards the center. The wind is deflecting towards the right. So this is right with respect to the wind per se. And sir, the wind is basically coming and deflecting towards the right and then converging towards the center. So if you see the direction of the rotation of the cyclone, so the direction of the rotation of the cyclone is anti-clockwise. That is why all the cyclones of the northern hemisphere, they rotate counterclockwise. And if we are trying to factoring in the direction of the the direction of the rotation of the cyclones in the southern hemisphere per se, so in southern hemisphere, the direction of the rotation will be how? Sir, the wind is deflecting towards its left and then spiraling towards the center. So the wind is deflecting towards the left and then it is spiraling towards the center. So the wind is deflecting towards the left and then spiraling towards the center. So the wind is deflecting towards the left and then spiraling towards the center. So if you see the direction of the rotation of the cyclone, so the direction of the rotation of the cyclone is basically clockwise. That is why all the cyclones of the southern hemisphere will be rotating in clockwise direction, and all the cyclones in the northern hemisphere, they will be rotating counterclockwise. So now if we are trying to understand what type of cyclones do we have, so depending upon how the low pressure core is induced, depending upon how the low pressure is actually induced, we can have two types of cyclones. So if the low pressure core is dynamically induced in the sense that if the low pressure core is induced on the basis of meandering of Rossby waves and jet streams, because Rossby waves and jet streams, they will be inducing series of high pressure and low pressure cells on the ground. So if the low pressure core is dynamically induced, we refer to it as cold core cyclones, or we call it as temperate cyclone. Or if the low pressure core is direct thermally induced in the sense that it is induced because of the sun's insolation, so we call them as warm core cyclone. So the temperate cyclones, they are also referred to as cold core cyclones, and the tropical cyclones, they are also referred to as warm core cyclone. So in UPSC up till now, you had a discussion of tropical cyclones many times, but I think that this might be the year when the UPSC will switch its gears and it will shift its focus on temperate cyclones, because temperate cyclones, they are nothing but western disturbances. So let us try to understand temperate cyclones in a great detail, because tropical cyclones anyway you will find everywhere, but temperate cyclones are not being covered in great detail. And frankly speaking, this is not covered in any of the NCERT, and this is not even covered in GCLEON. So you might treat my lecture as the only source of all of this. So let us try to understand what are basically temperate cyclones. So temperate cyclones, they are also referred to as mid-latitudinal cyclones. We also refer to them as traveling depressions, or we also refer to them as extratropical cyclones or wave cyclones. So extratropical or wave, tropical, extratropical, why? Because they are originating upwards of 30 to 35 degrees north and upwards of 30 to 35 degrees south. So sir, what is the difference between the temperate and tropical cyclone? Sir, in temperate cyclone, the diameter is close to 500 to 1000 kilometers. It's pretty big. So that is why temperate cyclones will not carry as much energy as the tropical cyclone. Why? Because the energy is well distributed across a great diameter. They are not power packed systems, unlike the tropical cyclones, and they typically go on for roughly 4 to 8 days. Some might go on for 1 to 2 weeks also. So there are actually 4 stages associated with what? 4 stages associated with the development, with the movement and the death of the temperate cycle. So let us try to understand and appreciate all of this in great detail as to how a temperate cyclone develops, as to how a temperate cyclone moves, and as to how a temperate cyclone eventually dies off. So if we are trying to understand and appreciate, sir, how do the temperate cyclones form and how do the temperate cyclones develop? So there are 4 stages. The first stage, it is referred to as the incipient stage. We also refer to is at stage 0. Sir, why do we refer to as incipient stage or stage 0? Because here you basically are having 2 contrasting air masses coming face to face and interacting with each other. So 2 contrasting air masses in the sense that, let's say you are having a maritime tropical air mass coming from the Atlantic Ocean and you are having a continental polar air mass coming from Siberia. These 2 air masses, they are coming face to face, they are not interacting into each other, they are not moving into each other. So if they are not interacting, they are not moving into each other because of same comparable intensity, so we can have the development of which front? We can have the development of stationary front, because the 2 air masses, they are not moving, they are not basically interacting with each other. So you are having a stationary front. Now after this, the next stage, it is referred to as embryo stage. Embryo stage meaning stage 1. So here if you are having two air masses, let's say you are having a warm air mass, so this is basically your maritime tropical air mass coming from Atlantic, and let's say you are having a continental polar coming from Siberia. If these two air masses, they are coming face to face, and above it you are having the passage of a Rossby wave or a jet stream. So if we apply the Ballot's law to the right hand side of the Rossby wave, you will be always having high pressure if you are in the northern hemisphere. So high pressure above, low pressure below. So now between these two air masses, you are having induction of a low pressure. So under the influence of meandering Rossby waves or jet streams, if between these two air masses you are having the induction of this low pressure core, what will happen? Sir, these two air masses, they will start spinning with respect to each other. So let's say that from basically the Atlantic, you are having a maritime tropical air mass coming in, which is a warm air mass. And from Siberia, you are having a continental polar air mass coming, which is a cold air mass. These two air masses, they were of same comparable intensity. That is why they were not moving into each other. Now, under the influence of a meandering Rossby wave or jet stream, you are having a low pressure core induced. So now, alongside this low pressure core, these two air masses, they are starting to spin. So the spin is basically anti-clockwise if you are in the northern hemisphere, and it is clockwise if you are in the southern hemisphere. Now guys, everybody focus on my hand directions because this is very important. So let's say I'm standing in the low pressure core. From my north, I'm having continental polar air mass coming, and from my south, I'm having the maritime tropical air mass coming. So if you carefully observe, from here I'm having cold air coming, from here I'm having warm air coming, and these two air masses, they have started to rotate in an anti-clockwise fashion. So now what is going to happen? Sir, out of these two air masses, which air mass has to work more? Sir, it's very simple. If cold air mass is coming, sir, the cold air mass has to rotate. It has to catch the warm air mass and toss it up. Why, sir? Because if we are talking about the interaction of cold air mass and warm air mass, the cold air mass has to toss the warm air mass above so as to move ahead, whereas the warm air mass, it just has to push the cold air mass from above and rise up and basically cool. So everything in the nature will be trying to achieve equilibrium. The cold air mass will try to move ahead, it will try to warm up, whereas the warm air mass, it will try to rise up and cool. So if I'm standing on the low pressure core, on my right hand side, you will be having a development of warm front, and on my left hand side, I will be having a development of cold front. The cold air mass is trying to push the warm air mass above, and the warm air mass is trying to push the cold air mass from above. So here I'm having warm front, here I'm having cold front. So essentially guys, what essentially is a temperate cyclone? So essentially temperate cyclone is nothing but what? It is nothing but a low pressure core around which two contrasting fronts, are rotating in anti-clockwise direction if you are in the northern hemisphere, and clockwise in the southern hemisphere. Now out of these two fronts, cold front and warm front, which front has to rotate more? Sir, but naturally the cold front has to rotate more. Why? Because the cold front has to catch up the warm front ahead and toss it up. It is as simple as this. So if we are trying to understand, sir, what essentially is a temperate cyclone? So essentially a temperate cyclone is a low pressure core around which two fronts, they are basically rotating. In which direction? Anti-clockwise if you are in the northern hemisphere, and clockwise if you are in the southern hemisphere. And if we try to decode, sir, which air mass or which front has to rotate more, sir, but naturally your cold front has to rotate more. So as the cyclone develops further, what is going to happen? Sir, the cold front has to rotate more. Why, sir? Because it has to catch up the warm front ahead and toss it up. So as the cyclone develops further, the cold front will rotate more and the warm front will not rotate that much. Hence, the next stage which we are having, it is referred to as what? It is referred to as mature stage, or it is referred to as stage number 2. In mature stage, the low pressure core is well developed. Sir, the two fronts are rotating properly. So now what can be the associated weather? Because this can be a very favorite question of UPSC. If you are trying to decode what is the associated weather, so in order to understand, sir, what is the associated weather under the cold front? So if we are trying to understand, sir, what is the weather under the cold front? So where do I have to stand? So I will have to stand in the warm sector, because then only I can see the cold front approaching. So if I'm standing in the warm sector, I can see the cold front approaching, and under the cold front, I can see the associated weather. Whereas if I want to see, sir, how is the weather associated with the passage of warm front? So I will have to stand where? Sir, I will have to stand in the cold sector. So all of us know that if I'm standing in the warm sector and if I'm trying to observe the cold front which is approaching, so cold front is almost perfectly vertical. So as the cold front is almost perfectly vertical, what is going to happen is that the air rises up abruptly. So as the air rises up abruptly, you will be having the formation of which clouds? So you will be having the formation of cumulonimbus clouds. So cumulonimbus clouds are associated with heavy rainfall, with very heavy snowfall. So if I'm standing at position number 2, wherein I'm having the passage of cold front, so under the cold front, what is going to happen is, sir, you will be having very violent weather. You will be having formation of cumulonimbus clouds with very heavy thunderstorm, with very hailstorm. But if I want to understand, sir, how is the weather associated with the warm front? So I will have to stand where? I will have to stand in the cold sector. So now warm front is relatively more inclined with respect to the vertical. The angle of repose is close to 1 to 5 degree. So that is why the air will rise up smoothly. So as the air rises up smoothly, what is going to happen is that you won't be having formation of thunderstorm clouds. You won't be having the formation of cumulonimbus clouds. Dare I say, you'll be having formation of such clouds which can cause light drizzle or light rainfall for a longer period of time. So instead of formation of cumulonimbus clouds, you can have the formation of nimbostratus clouds. So nimbostratus or stratonimbus clouds, black colored clouds, low level clouds, middle level clouds, which can give light to moderate rainfall for a long period of time. This is what happened on 11th of July 2019. Mahendra Singh Dhoni ji was batting against New Zealand in Lords, and suddenly a cold front came and we lost the match basically because of that. So now, if we are talking about the mature stage, sir, what is going to happen in the mature stage? Sir, this cold front from behind, it is going to catch up the warm front ahead. If I'm standing over here and if I'm trying to see this picture, so what I'm going to see, sir, on my left, I'm going to see cold front, and on my right, I'm going to see the warm front. So on my left hand side, I'm having the cold front. On my right hand side, if I'm having the warm front. So on my left hand side, I'm having cold front. On my right hand side, I'm having the warm front. Slowly, sir, the cold front from the left, it is going to catch up with the warm front on the right, on the ahead, and it is going to catch up and toss the warm sector above. So in mature stage, the cold front from behind is slowly catching up with the warm front ahead, and eventually, sir, your cold front catches up with the warm front. So as soon as your cold front catches up with the warm front, what happens is, sir, your entire warm sector is tossed up. So if I'm trying to basically make you understand, sir, what happens in the last stage. So the last stage, it is referred to as occlusion stage. Sir, occlusion stage in the sense that the cold air mass from behind, it has actually catched the warm front ahead and it has actually tossed it up. So as soon as the warm sector is completely tossed up, the front is no longer in contact with the ground. So as the front is no longer in contact with the ground, there will be no frontal interaction. And that is why this stage is referred to as the occlusion stage or frontolysis. Frontolysis in the sense that warm sector is completely tossed up. The front is no longer with the contact with the ground, and that is why we have the formation of occluded front. The occluded front is represented by alternate teeth and saw. So as soon as we have the formation of occluded front, we refer to it as what? We refer to it as frontolysis, the death of the front. The death of the front in the sense that basically your temperate cyclone will now die. Why? Because your interaction is over. So stage number 1, it is referred to as what? Sir, stage number 1, which is referred to as the incipient stage, it is referred to as frontogenesis, because here you are having birth of the temperate cyclone. And sir, the last stage, it is referred to as frontolysis, the death of the temperate cyclone. Till when? Till again new fresh air masses are created. So now that you have understood through diagrams, let me showcase you the actual meteorological representation so that all of you get confidence, because this question I am expecting that you might get in this year's mains. So this is very important. Let us try to figure this out. So see, I'm just showcasing you, sir, how do we have the stages of basically the temperate cyclone? Sir, what is the actual meteorological representation? So see, stage number 1, it is referred to as stationary front. You are having a cold sector, you are having a warm sector existing together. They are not moving into each other. You are having stationary front. The air is dilating along the axis. Sir, as the low pressure core is induced, sir, the two air masses, they start to spin around each other in anti-clockwise direction if you are in the southern hemisphere, and clockwise direction if you are in the southern hemisphere. So sir, on my left hand side I am having the formation of cold front, on my right hand side I am having the formation of warm front. Sir, as the cyclone develops further, the cold front has to rotate more. Why? Because it has to catch up the warm sector ahead and toss it up. Sir, slowly the cold front from behind, it catches up with the warm sector ahead, and sir, as soon as it catches up, you are having the formation of what? You are having the formation of occluded front. So eventually the front dissipates, and then sir, this low pressure core gets cut off. So this is referred to as what? This is referred to as the cutoff cyclone. So this process will repeat again when, so this process will repeat again till two contrasting air masses again come face to face and the low pressure core gets dynamically induced. Okay, sir. So now if we are trying to figure it out, basically that when we are trying to understand and appreciate, sir, where we can have the movement and the formation of temperate cyclones. So the movement of temperate cyclones is such that in general the temperate cyclones will be carried by what? Sir, in general the temperate cyclones will be carried by the Rossby waves and jet streams. So can I say that in general the movement is from west to east? Definitely, sir, because the Rossby waves and the jet streams, they are upper tropospheric winds. Upper tropospheric winds are oriented perfectly westerly at all the latitudes. Definitely, sir. But sir, it might happen that the meandering becomes very sharp, because ultimately Rossby waves and jet streams, what is their primary role? Sir, the primary role of Rossby waves and jet streams is basically the energy distribution from the equatorial and tropical latitudes towards the polar latitudes. So if you talk as to what is happening today, so as of today, the energy distribution or the heat exchange of Earth itself is in shambles. The polar regions are warming more, and sir, as the polar regions are warming more, what is going to happen? Sir, as the polar regions are warming more, but naturally, sir, the heat distribution from the polar latitudes towards the equatorial latitudes is increasing. As it is increasing, sir, the meandering also becomes very sharp. So if the meander is becoming very sharp, what can happen is, sir, the Rossby waves or the subtropical westerly jet, it can drag the temperate cyclones from the north towards the south. So the temperate cyclones can get dragged, and as they get dragged, so if a temperate cyclone is coming towards the equatorial or the tropical Atlantic? Sir, the northeast trade winds, the easterlies, the trade winds, they can basically throw the temperate cyclones where? Towards Gulf of Mexico. So if the temperate cyclones get dragged towards the equatorial latitudes, towards the tropical latitudes, they can get intercepted by the trade winds, and they, instead of moving from west to east, they can move from east to west. This is all happening because of what, guys? This is all happening because of climate change, global warming. Or else they can be dragged towards where? So they can be dragged towards India, where they are intercepted by the Himalayas. So the weak temperate cyclones coming from the Mediterranean region, from the Black Sea, from the Caspian Sea, which are actually intercepted by the Himalayas, and because of which we are having winter rains, it is referred to as what, guys? It is referred to as western disturbances in reality. So western disturbances are actually very necessary for the ripening of wheat crop, for the ripening of kharif crops. But today what we are finding is, because of global warming and climate change, sir, the western disturbances themselves have become very erratic. They have become very intense and less frequent. So western disturbances is because of what? We get snowfall in the upper reaches of Kashmir, we get winter rains, but today the western disturbances, they have become very intense and less frequent. So the Kashmir is going snowless. Sir, we are finding western disturbance influence in central India and peninsular India also. Why? Because of climate change and global warming, because of the meandering of the Rossby waves and jet streams. So the index cycle is getting heavily disrupted. This question can also come in this year's mains. Very important. Okay, sir. But sir, if you are trying to figure out, sir, what is the preferred location of the origin of the temperate cyclone? If we are trying to figure out what is the preferred location of the origin of the temperate cyclones, so the preferred location is the permanent low pressure cells of the northern hemisphere. So we, all of us know that the subpolar low pressure belt of the northern hemisphere is not a continuous pressure belt, it's rather discontinuous. And instead of continuous pressure belt, we find continuous pressure cells or discontinuous pressure cells, which are permanent on water, because water is going to have very high specific heat retention capacity. So we are having Alberta low, we are having Aleutian low, we are having Icelandic low, Baltic low, Barents low, Bering low. These are basically your permanent low pressure cells on water in the northern hemisphere. So this is the preferred location of the origin of what? Of the origin of the temperate cycle. Please understand and appreciate this. This is very, 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 very important. So you can be asked question as to how the temperate cyclones are basically resulting into erratic weather in India. Your simple answer is that, sir, temperate cyclones, they are nothing but traveling depressions, and as their intensity has become very high, sir, we are expecting cold fronts coming in India up to peninsular and southern regions also. Very, 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 very important. Okay, so let us get the last part of today's lecture, because this question again I am expecting that you can be asked in mains. So let us try to understand the importance of coral reefs, because this is very, very important. Let me just open it that we can understand and appreciate this. Sir, what are coral reefs and why it is so important? Because last year the question was, sir, why sea level rise is resulting into increased cyclonic activity? The answer is very simple, because the cyclone, the tropical cyclone, derive their energy from the latent heat of condensation. But now we can understand, sir, what are the consequences of marine heat waves? So marine heat waves, in the sense that how much heat is trapped in the upper 2000 meters of sea water. So I'm giving you very latest data so that all of you can appreciate it. So we refer to it as ocean heat content anomaly. So this is basically the data given by NOAA, National Oceanic and Atmospheric Administration, which works under NASA. So a very recent data I'm all giving you. Please understand, appreciate this, and you can utilize it in this year's mains also. Those of you who will be writing the answers, try to understand this data very clearly. So this is basically your global ocean heat content in the upper 2000 meters. Please understand that this is very recent data of 2025 also. So on your y-axis, you are having ocean heat content anomaly. Sir, ocean heat content anomaly in the sense that waters, because of their high specific heat, they should be able to trap the excess heat on Earth, meaning that the temperature of the ocean should not rise. They should act like a carbon heat sink. So the ocean heat content anomaly, it is expressed in zeta joules. So zeta joules in the sense 10 raised to power 21 joules. And on your x-axis is your annual mean according to years. So what does this graph indicate to each and every one of you? Sir, this graph indicates that up till 1990s, late 1990s, sir, the annual mean was zero. Annual mean was zero in the sense that whatever heat the oceans were absorbing, it was not resulting into increase in temperature of the oceans. So the net heat exchange was below zero. But after 1990s, what we are finding is that the oceanic heat content is continuously increasing in the sense that the waters, they are no longer acting as heat sinks, they are rather acting as heat engine, they are rather acting as heat emitters. So if you talk about 2025, sir, in 2025, the global ocean heat content has crossed more than 300 zetajoules in the upper 2000 meters. Why? Because of anthropogenic emissions. We are emitting more and more CO2, we are emitting more and more methane, we are emitting more and more greenhouse gases. So the oceans today, they are acting as heat sinks. 90% of the excess heat which humans are pumping, it is going where? It is entering into the oceans. So because of this only, we are having marine heat waves. The average temperature of the oceanic surface is well beyond 2 degree or 5 degrees Celsius also in some of the locations. So now because of this, what is going to happen, sir? So all of us know that if I'm talking about coral reefs, so what coral reefs actually are? So coral reefs, they are nothing but the landforms, they are nothing but the skeletal accumulations of a marine organism called as coral polyps. So if I'm just showcasing you, how do coral polyps look like? So coral polyps, they are basically heterotrophs. So they are basically skin colored organisms. They basically trap the fish using their tentacles. So in order to trap the fish using their tentacles, the fish must get attracted towards it. So how they can attract the fish? So they get colors because of what? They get colors because of a marine algae called as zooxanthellae, which is capable of doing photosynthesis. So if you typically see, sir, how do coral reefs look like? So coral reef, basically they are very much colorful. They are very much, sir, endowed with marine life. So you are having the coral polyps. Sir, this coral polyps, they are basically getting good color. Sir, good color because of what? Because of a marine algae called as zooxanthellae. So if I'm in a nutshell, if we are discussing what are coral reefs, so coral reefs, they are nothing but the landforms of skeletal accumulation of a marine organism called as coral polyps. So this coral polyps, it lives in a symbiotic relationship with a marine algae called as zooxanthellae. So the marine algae imparts colors because it is capable of doing photosynthesis, and in return, the coral polyps is basically giving support structure. So the marine life gets attracted towards it, and that is why the coral reefs, they are referred to as what? Sir, the coral reefs, they are referred to as the rainforest of the oceans. This is very important. They are referred to as what, guys? They are referred to as the rainforest of the oceans. If we are trying to understand, sir, what are the conditions which are responsible for the coral reefs? So the first condition is basically that they should have good insolation. They should exist in photic zone. So maximum depth which you find where? it is close to 80 fathoms, close to 100 meters. So 1 fathom close to 1.89 meters, the the nautical mile unit. So the first is that the algae should get appropriate sunlight. So maximum coral reefs which you will find, they will be basically in the first 100 meters. In the world, you do find deep sea corals, which are basically exception, which are found more than 4,000 meters in depth. So they don't source the nutrients from the sunlight. They actually source the nutrients from the deep sea currents, which are referred to as a thermohaline currents. So this is very first condition which is necessary. So the second condition necessary is that they require an ideal sea surface temperature of 27 degrees Celsius. Sir, 27 degrees Celsius, why so? Because see, this symbiotic relationship is extremely temperature sensitive. Even if you have more than 1 degree or 1.5 degree of variation, what happens is, sir, the coral polyps, they start excluding the marine algae. So the marine algae is thrown above in the sense that it's completely excluded. It disrupts the symbiotic relationship. So this is condition number 2 which is necessary. After this, basically the third condition which is necessary is that the coral reefs, they cannot grow in muddy waters. They require fresh turbulent waters, and they are typically associated with what? They are typically associated with warm tropical saline waters. They require flowing waters. They require good flow of nutrients, and that is why wherever you will be having warm ocean currents. So warm ocean currents are property of what? Warm ocean currents are property of tropical western waters. Tropical western waters in the sense tropical eastern coasts. So that is why the coral reefs, they are never found where? They are never found in the upwelling zones where you are having the cold oceanic waters being continuously upwelled, in the cold current zone, in the equatorial zone, in the margins of Atlantic and the margins of Antarctica. You will be always finding basically coral reefs where, sir, you will be always finding coral reefs on the tropical western waters where you are having warm ocean currents. So here you are having Gulf Stream or North Atlantic Drift. Here we have, sir, Brazilian current. Here we have Mozambique current. Sir, here we have the Eastern Australian current. And they will be never found where? They will be never found in the cold current zone where you are having ocean water upwelling. So Humboldt current, California current, Canaries current, Benguela current, they are never found in these zones. Why? Because cold currents, they will typically result into negative anomaly of temperature. And last but not the least, if we are trying to understand, sir, where will the coral reefs grow? Sir, the coral reefs will typically grow towards the open seas. They will never grow in the lagoon side. So they require flowing waters. They require basically fresh water. They don't require stagnant waters. They require turbulent waters. So now let us try to understand a very important component called as coral reef bleaching, because this is very, very important. Now coral reef bleaching in the sense of what? Sir, coral reef bleaching in the sense that your symbiotic relationship actually breaks. So as soon as your symbiotic relationship breaks, then what happens is that, sir, your zooxanthellae algae is basically expulged out. Expulged out in the sense that the zooxanthellae algae is completely thrown out. And as soon as it is thrown out, what is going to happen is that your photosynthesis completely stops. So as your photosynthesis completely stops, sir, the coral reefs, they will be not able to have the colored look. So they will all get a bleached look. So as soon as they get bleached looked, the marine life is no longer attracted towards it. And sir, your entire reef system becomes devoid of life. If I'm just showcasing you how does a bleached coral look like. So see, this is how basically your bleached coral look like. Completely devoid of life. It's completely haunting that, sir, how do bleached coral look like? Just get a good picture of it. Yeah, I guess this is more convincing image. Yeah, this is a more convincing image. So if you see this image, you can clearly see the pores of the coral reefs open. They don't have zooxanthellae algae. And sir, the entire reef system is devoid of marine life. So there is an organization called as CRW. So CRW stands for Coral Reef Watch. So Coral Reef Watch, it works under NOA, National Oceanic and Atmospheric Administration, which works under NASA. So according to CRW, since 1989, we basically had 4 mass coral bleaching incidences. Mass coral bleaching incidences. So globally, when more than 60 to 70% of the corals totally in the world get bleached, we refer to it as mass coral bleaching. So one we had in 1989, another we had close to in 2000, then we had in 2016 and 15, and the latest one is from 2023. So 2023 till present, as I am taking this lecture, sir, the coral reefs are being bleached. It is still continuing. We are now living in the 4th coral mass bleaching incident. So sir, what are the reasons behind this? That why do we have the coral reef bleaching? So please look at this slide very, very carefully, guys, because I am expecting one question from this slide seriously in this year's mains. So number first reason, of course, the potato, like aloo, जो आप हर किसी सब्जी में डाल सकते हो, right? So global warming. So as we are pumping more and more greenhouse gases, the heat content of the oceans is increasing. So as the heat content of the ocean is increasing, we are going to have marine heat waves. So the sea surface temperature is rising, but naturally, sir, the symbiotic relationship is going to break. So today, majority of the coral reef bleaching that is happening, it is happening because of what? It is happening because of this only. So the biggest reef system in the world, the Great Barrier Reef, it has been bleached permanently to the tune of 60 to 70%. 70% of the Great Barrier Reef is lost today. Very bad. Then, sir, as we are pumping more and more CO2, it is sequestrated or it is absorbed in the oceans. Because of this, sir, you are having ocean water acidification. You will be having creation of bicarbonate ions. You will be having creation of carbonic acid. So as carbonic acid is formed, the pH level drops. As the pH level drops, the ocean water becomes acidic. It starts dissolving the corals itself. So the coral reef structure collapses, and you do not have enough calcium salts to basically make the exoskeleton, because the bicarbonate ion will basically start reacting with calcium in the oceans. So there will be less calcium for the corals to basically make their exoskeleton. So number 2 is this. So number 3, of course, ocean water chemistry. So now you know on the west coast of Kerala, a ship has sunk carrying very hazardous chemicals. So pollutants, heavy metals, mercury, arsenic, lead. Then you can have domestic discharge, tide, सफेदी की चमकार, surf excel दाग अच्छे हैं. अरे, all of this water is entering where? It is entering into the oceans. So the nutrient rich water with nitrates and sulfates, as it enters into the oceans, you are going to have harmful algal bloom. So harmful algal bloom, sir, your biological oxygen demand, it increases, and sir, your dissolved oxygen level, it decreases. Your marine life will start suffocating. Very naturally, sir. And sir, you can have bacterial or viral outbreaks like we had in the Mediterranean Sea, the bacterial outbreak of E. coli. And sir, we can also have invasive alien species. Sir, introduction of non-native species, because of what? Because of ballast water pollution. Sir, what do you mean by ballast water pollution? Can you just explain us this? Yes. So see, if I'm talking about ballast water pollution, so see, this is referred to as ballast of ship. So whenever a big container ship or whenever a big cargo ship is floating in the open seas, let me just get a good image. Yeah, you can understand it through this image. So let's say this is a big container ship or a big cargo ship. So let's say a ship is coming from Dar es Salaam, the biggest port on the east coast of Africa, and it is coming to Mumbai. If it is unloaded, so what do the ships do? They basically load the water into the hull, into the ballast of the ship, so as to increase its weight, so that they can attain great stability. And once the ship reaches Mumbai, it is going to empty this, because it is going to get loaded with oil, it is going to get loaded with cargo. So the water which is being emptied, it is going to carry pathogens, it is going to carry non-native species from which side? From the Africa's east coast. So this is referred to as the invasive alien species. So guys, this is very important, and I'm guessing that you might be getting one question from this. Okay. So guys, this sums up the part where I have discussed the important geophysical phenomenon with all of you. Now you will be getting one more lecture from me, wherein I'll be discussing the complete physiography of India. We'll be discussing the river system, we'll be discussing the orientation of mountains that we have, and the associated climate and the vegetation. Okay. So on the behalf of StudyIQ, I thank each and every one of you. Please remember to follow me on Telegram. So I am the head of department over here for Geography, Environment and Ecology. So all of you can follow me on Telegram. My official handle is CSE with PM, and of course you can follow me in all the videos out there. Okay. On the behalf of StudyIQ, Tata, bye bye, adios amigos. Please keep on working hard. Please keep on working smart, because that is the ultimate need of this examination. So today you must have got a good trailer as to how you need to approach the mains. There is a stark difference between prelims and mains. In mains you need to be specific. In mains you need to be to the point. That is why in my entire lecture I did not speak even one part which is out of the syllabus. I have stuck to the syllabus, and this is what is needed in mains. So please, it's a request on the behalf of myself and on the behalf of StudyIQ, please work hard, please work smart, and come out with flying colors, and please take our country ahead. Okay, thank you everybody. Good night. I will see you all on the other side. Bye bye.